Good morning everyone. This is Avaris Aditya Bharadwaj, branch CA 24BQ180410. Today's subject is probability theory and stochastic process. My topic is power density spectrum and its property, cross power density spectrum and its properties. Power spectral density (PST). The definition of power spectral density is the power spectral density (PST) of a WSS random process. X of t is defined as Fourier transform of its autocorrelation function or xx of tau. Here Rxx of tau is autocorrelation function. This power spectral density PST is defined as Sxx omega is equal to minus infinity to infinity Rxs of tau into e power minus j omega t dt. The inverse relationship is also true. The autocorrelation function can be obtained from the PST power spectral density using the inverse Fourier transform. That means Rxx of t is equal to 1 by 2 pi integral minus infinity to infinity Sxx of omega into e power j omega t d omega tau d omega, and the power spectral density and the autocorrelation function are Fourier transform pairs. And here are some note points. If x of t is a real process, then both Rxx of tau and Sxx of omega are real functions and even functions. That means Rxx of tau is equal to Rxx of minus tau. Sxx of omega is equal to Sxx of minus omega. Definition: that means alternative form is the power spectral density can also be defined as xs of omega is equal to limit t tends to infinity. See here, t tends to infinity into expectation of modulus of xt of omega whole square by 2t. Here xt of omega is for a transformer, we know that. And now here properties of power density spectrum. Property number 1, s xx of omega greater than or equal to 0. Yeah, now let's see the proof. From the definition, the expected value of a non-negative function e of modulus of xt of omega whole square is always non-negative. So whole square non-negative. Hence s xx of omega greater than or equal to 0. Now property number 2, the power spectral density at 0 frequency is equal to the area under the curve of autocorrelation Rxx of t. That is Sxx of 0 is equal to integral minus infinity to infinity Rxx of tau dt. Proof. Yes, now here we see the proof. From the definition we know that Sxx of omega is equal to integral minus infinity to infinity Rxx of tau into e power minus j omega t d tau. At omega is equal to 0, Sxx of 0 is equal to integral minus infinity to infinity Rxx of tau d tau. Now here, let's see the property number 3. Property number 3 states that the imaginary part of Sxy of omega and the imaginary part of yx of omega are odd functions of omega. That is imaginary part of, and this is in mathematical form imaginary. Im indicates the imaginary. Here Im indicates the imaginary part. And let us go with proof. Yeah, here that is imaginary part of sxy of omega and imaginary part of syx of omega are odd functions. Let us go into proof. Consider sxy of omega is equal to integral minus infinity to infinity rxy of tau into e power minus j omega t omega tau d tau. Yeah, let's see here. Sxy of omega is equal to integral minus infinity to infinity rxy of tau. Here we write this e power minus j omega t as cos omega t minus j sin omega, cos omega tau minus j sin omega tau d tau. And now imaginary part of sx of omega is equal to sy. Xy of omega is equal to integral minus infinity to infinity rxy of tau into minus sin omega tau d tau. It is equal to integral minus infinity to infinity rxy of tau into sin omega tau d tau. Now that is equal to imaginary part of xy of minus omega is equal to minus integral minus infinity to infinity rxy of tau into sin minus omega tau d tau. Here integral minus infinity to infinity rxy of tau into minus sin omega t d tau. Hence we can say that imaginary part of sx of y omega is an odd function of omega, and it is also, and here imaginary part of s y of x is also an imaginary odd function. Property number 4. Sxx of omega is also a real function, always a real function, as it's a very simple proof. Sxx of omega is equal to limit t tends to infinity e expectation of modulus of xt of omega whole square by 2t. Since the function modulus of x of t omega whole square is a real function, Sxx of omega is always a real. Now we will discuss about cross power density spectrum. Definition. There are two definitions. Consider two real random processes x of t and y of t. If x of t and y of t are jointly wide sense stationary, that is known as WSS random process, then the cross power density spectrum is defined as the Fourier transformer of the cross correlation function x of t and y of t. It is expressed as s xy of omega is equal to integral minus infinity to infinity rxy of tau into e power minus j omega tau, and s yx of omega is equal to integral minus infinity to infinity ryx of tau into e power minus j omega t dt. By inverse Fourier transformation, we can obtain the cross correlation function rxy of tau is equal to 1 by 2 pi integral minus infinity to infinity sxy of omega into e power minus j omega t d omega, and ryx of tau is equal to 1 by 2 pi integral minus infinity to infinity syx of omega into e power minus j omega t d omega. As we know that, therefore the cross power density spectrum is known as PSD, and the cross correlation function are Fourier transform pairs. Definition 2. If x of t of omega and y of t of omega are Fourier transform of x of t and y of t respectively in the interval of minus t to t, then the cross power density spectrum is defined as Sxy of omega limit t tends to infinity expectation of x of t xt of omega cross correlation. We use this symbol y of t of omega by 2 pi, and same yx of omega. Here we use x, we replace x with y with x. The same formula will obtain by replacing x with y and y with x. The formula also replacing by x with y and y with x. Here some of properties of cross power density spectrum. The first property is Sxy of omega is equal to Syx of minus omega is equal to Syx of omega. Proof. Consider the cross correlation function Rx of tau. The cross power density spectrum is given by Sxy of omega integral is equal to integral minus infinity to infinity Rxy of tau into e power minus j omega tau d tau. Let tau is equal to minus tau. Then Sx of omega is equal to integral minus infinity to infinity Rxy of minus tau into e power minus j omega t d2. Since we know that these both are equal, hence we replace this Rxy of minus tau is equal to Ry of x tau, and we obtain this property. And here second property, the real part of Sxy of omega and the real part of Sy of omega are even function of omega. That means these both are even function. Hence we know that we are here to prove this property. Yes, we know that Sxy of omega is equal to integral minus infinity to infinity Rxy of tau is into e power minus j omega tau. We know that e power minus j omega tau is equal to cos omega tau minus j sin omega tau. We see in previous power density spectrum previous topic. Same formula. And by substituting this in this equation, we get integral minus infinity to infinity Rxy of tau into cos omega tau. As we know that cos omega tau is equal to cos of minus omega tau. That is cos of theta is equal to cos of minus theta. So real part of Xy of omega is equal to real part of Xy of minus omega. So it is an even function, and therefore by replacing x with y and y with x, it is also an even function. And let's see the property number 3. The power density spectrum of real process x of t is an even function. That means Sx of minus omega is equal to Sx of omega when x of t is real. As we know that Wss is a real process, we know that formula integral minus infinity to infinity Rx of tau into e power minus j omega tau d tau. As we put omega into in the place of minus omega, minus omega in place of omega, we just have this e power minus j omega tau in plus. So integral minus infinity to infinity Rx of tau into e power minus j omega d tau. Hence tau is equal to minus tau. S dash of x of minus omega is equal to integral minus infinity to infinity minus tau into e power minus j tau. So Rx of minus tau is equal to Rx of tau. Therefore, by substituting this, we get Sx of minus omega is equal to Sx of omega. And the last property is if they are orthogonal. If they are orthogonal, then Rx of tau is equal to Ryx of tau is equal to 0. We know that Sxy of omega integral minus infinity to infinity Rxy of tau into e power minus j omega d tau. So these both are 0, and we prove that Sxy of omega is equal to 0 and Xyx of omega is equal to 0 if x of t and y of t are orthogonal. Thank you. 24BQ 180410.